So if you talk about the classifiers that you might see with, say, a VMM winner-take-all structure, you might ask a question of how well would this work, and what does the sort of physical details look like as I get into this? In particular, imagine if I were to build multiple of these, how similar are they as I work through all of this? So part of that question would be, well, imagine if I had this in an FPA device and I compiled it in a few different places. So I might just use a couple different components to put it in one spot versus another spot versus a third spot. And I could use different pieces for different reasons. Okay. So imagine I were to put these in different places, and that just kind of how the transistors that I have and where I needed to put them. But I put them spread out enough so that you can see that there's some variations to it. At one level, I am creating a crossbar. Usually this is going to be pulled out of routing fabric. And the conversation would be, okay, now I'm going to have 2 inputs plus a constant, and then I have 3 output currents because I'm going to have 3 metrics that I'm creating that I want to take a look at and see how it approaches. And so you might think to yourself, okay, that would make some sense, right? And I'd like it if I put it in all of these positions, I'd like it to give me the same result. Well, what is coming out of this is these currents then go into a winner-take-all. This is a very typical Lazaro type of winner-take-all structure. There is a current source from this VS down to ground. That wasn't actually drawn in this picture originally. So there's a current source and FET transistor down there to constrain all of these source nodes. And therefore I have these inputs. I effectively have these outputs, which are now voltage outputs, and I actually have floating gates sitting here to set those. Those also show up in the routing fabric. Now, I could have put a lot of this into one cab, easy enough to do this in a couple cabs and then just route as needed. And then have a single current source, which I believe is what was put in these single points at the bottom. Now, to think about this, you might say, well, first, how do I transform the weights? And what's really nice is that there's some transformational properties that allow me to do some invariance, do some scaling, and allow everything to be one quadrant multiplications because of the beautiful common mode rejection properties of the winner-take-all structure. It's a generalized approach. So what I would imagine is I could imagine theoretically having 2 inputs plus, say, an offset, which could just be a 2.5 volts and a 2.5 volt supply device. Thinking about this for the first system on chip FPA devices, which had a 2.5 volt supply, 350 nanometer process. And what you see is that, okay, here's where my 3 vectors, one is going to be one at all zeros, one at 2 and 2 with an offset of -2, and one at 1, 1, which kind of gives you that sort of push in the middle, which pushes the exclusive OR structure that you're looking for. Okay? And so you say, well, how do I look at this in practice? Well, I'm going to then say, well, I really would like to have ideally, now put this in currents. Now it's maybe 50 nanoamps, 25 nanoamps, and sort of still at 0 with then the offset. So I just scale this accordingly. Right? So now my bias current is basically 25 microamps is equal to 1. There's a scaling term that goes on here. Well, my actual values may actually be slightly different because of how I programmed it, or may not be perfect. And again, there can also be mismatches due to indirect programming. If you didn't compensate for it, if you did, again, it's an interesting thing to see the differences and just make sure that you can get it to work. But you might get something that's slightly different in terms of some of the numbers. And I think these 2 numbers were swapped in the offset, so just kind of notice that from here to here. So what you end up getting then is like it may be slightly different, but it should still hopefully work. And if you were to say, let me scale through a whole bunch of the numbers, going from zeros to 1, sort of 0, 1, 1, 0, and then 1, 1, you would end up seeing what the typical temporal result is. Done in seconds, just to kind of keep it nice and simple and slow. I'm not making any conversations at speed, and you notice it's pretty much perfectly fast. So what's interesting is that for the different two of the other elements, or the null elements that we're not using, you notice you get one that gives you a very interesting output with basically you get a response but then zeros everywhere. The other one you get basically no response and then zeros here. So you might think, those also look like logic gates. And it's actually kind of a neat thing if you kind of think about what those two mean. And I leave that as an exercise for the viewer. But notice this one actually gives me an exclusive OR, where actually down would actually give you a 1, and the zeros are the high ones are actually nothing happened. Here's the interesting thing, is that I can take this in all these different spots, and because it's just a matter of making this matrix look ideally to this, to reprogram it, I can take it done in 3 different places and reprogram it and then modify that to then give me all 3 of the XOR patterns perfectly as I would want. So it's one of the beautiful things of the floating gate elements is not that I've just created just a single pattern, but that I can create it anywhere. And if I account for, in this case, it's just going to be the indirect programming mismatches, but most of the time I can build architectures to even get rid of some of that. All of a sudden, this is pretty much looks like what I would theoretically expect. And this is not how you typically think about analog, but this is what not only you need to have, but also what you can do with programmable analog systems.